Hello everyone, let's wait for 5 more minutes, then we can start the session. Okay, I think we can start the session. So, hello everyone, welcome to today's live session. So, this is live session number 5, and I am your TA for this particular session. My name is Arpit Bal, and I am a PhD scholar from Department of Electrical Engineering, IIT Bombay, and I am a PMRF scholar. And in the previous lectures, what we have covered is related to basics of number system, then basic logic gates, floating point representation, and few basic uh, arithmetic circuits. So in today's session, what we are going to cover is related to some more arithmetic circuits. We will have some combinational circuits like mux, decoders, encoders, like that, and we will try to solve some problems related to that, which will help you in solving your assignments and to have a better grasp over the concepts. And so for today's session, what I have done is, so the mic is available, so whenever you have a doubt, you can just unmute yourself and try to ask me the question, and I'll reply you over there. So yeah, so can anyone try the microphone if it is working fine?
Yeah, it is.
Okay, thanks for confirmation. Okay, let's start with today's session then. Okay, so the first question is, we have to find the number of 2 cross 1 mux that is required to implement 16 cross 1 mux. So what we are having is, we have a set of a bunch of 2 cross 1 mux, and we have to implement a 16 cross 1 mux using those 2 cross 1 muxes, right? So So in these type of problems, what we need to do is we need to first check what is the number of inputs that the new mux should have. Alright, so the new mux should have 16 inputs. Okay, so if we have total 16 inputs, then at the input side, how many 2x1 muxes we will need? Okay, so 2x1 mux, it means there will be 2 inputs, right? So how many 2x1 muxes at the input side will be needed to cover 16 possible inputs? It is 2 into x is equal to 16, so it means we will need 8 muxes, right, at the input side. So let me arrange those muxes. 0, 1. Similarly, let me call it 2, 3, so on and so forth, till we have 6, 7. Sorry, till we have 14, 15. Okay. So these are total. Let me number the muxes as well. Number 1, number 2. It will go till number 8. Okay. So we have total 8 lines coming out of these muxes. And we need to multiplex these 8 lines. So we have 8 lines. So now you can treat it as that total 8 lines are present. And you have a bunch of 2x1 muxes available with you. And you need to multiplex them. Okay. So 8 lines. And we have 2 input muxes, so it will be 8 by 2. Yeah, so it will be 8 by 2 is equal to 4 muxes, right? So here we will need 1, then another mux covering another set of input. This will be coming from input mux number 7. This will be from mux 1 and mux 2. Okay, so here how many muxes are there? 4 muxes. Here how many muxes we had? 8 muxes, right? So from the 4 muxes, how many output we will have? We will have 4 outputs, right? So these are 8 lines. These are 4 lines. So these 4 lines we further need to multiplex, right? Then 4 by 2 is equal to 2 mux. So this will be 1 mux. Similarly, there will be another mux. And at the end what we will have is we will have the outputs from 2 multiplexers. 2 multiplexers, it means 2 output lines, right? So for the last remaining 2 line we can just put a single multiplexer. Okay, so here we have total mux is equal to 2. Here we have 1. So total number of multiplexers that we need is, at the input we needed 4. At the intermediate stages we needed 4. At the input we needed 8. At the intermediate stage we needed 4. Then we needed 2. And then we needed 1. So total it is 15 muxes. Okay. Is the procedure clear? Does anyone have any doubt in this question? Okay, if not, then we can move forward. Okay, so next we are given a circuit and we need to figure out the Boolean expression that is implemented by this circuit. So the best part about muxes is we can implement any function, any logic using muxes and inverters, right? So here we are trying to implement this big function. If we had not used muxes, then we would be using the basic gates. Yeah, muxes are built from basic gates, but they kind of provide us a level of abstraction that you have the muxes, you can directly start on constructing the circuits. Okay, so let me mention one thing here. So let's say you have a mux. Okay, 0 and 1 are the input, and let's say the select line is S, and 0 takes input A and 1 takes input B. Okay, and you have the output named as out. So the equation for this mux will be out is equal to S bar A plus SB. Okay, so try to remember this, because this will be helpful in constructing bigger and bigger expressions, right? So how did we come up with this expression? So let us say S is equal to 0. Okay, so if we select S is equal to 0, then the output will be A, right? So that's why I wrote S bar into A. So S bar is high when S is equal to 0, right? Then I wrote plus S into B. So when S is equal to 1, then B is selected, right? But when S is equal to 1, A should not be selected. So what happens is this bar takes care of that thing. So it means from the output, at a particular instant of time, only one of the inputs, it finds its route to the output, right? So this is how we are going to use the muxes for constructing bigger and bigger expressions. So for this particular question, let us try to, let us name the nodes. Let me call this node as A. Okay, so let us try to get the equation at node A. So this, let us treat this one as reference. Okay, so node A is equal to x bar dot y plus x dot 0, right? So when x is equal to 0, it will choose y. When x is equal to 1, it will choose 0. So we have, this implies A is equal to x bar y. Okay, so that is the equation for A. Similarly for F, we will have, so this node is A, and here A passes through an inverter, so this is A bar. So F can be written as z bar A plus z A bar, right? Now let us replace A with the actual equation. So we will have z bar x bar y plus z x plus, I wrote it directly, let me write it like this, plus z x bar dot y whole bar. Okay, so we will have x bar y z bar plus z. Okay, so here we can use De Morgan's law. So we will have x plus y bar. Okay, so we can write it as x bar y z bar plus x z plus z y bar. Okay, so this is our option B. Right. So is this question clear? The method how we solved? And so always remember this particular equation, so you can solve any bigger mux circuit using this reference equation. Okay. Does anyone have any doubt in this question? So if you have a doubt, you can unmute yourself and let me know. Okay, so let me give a small assignment problem which you can try on your own. So let us say you are having a two input. So let's say there's a block which takes two inputs, A and B. Okay, so and it implements a function f is equal to summation of 0, 1, 3. Okay, so try to implement this function using multiplexers. Okay, so this you can take it as a short exercise. So using whatever problems that we are solving in this particular session, you should be able to solve this. If you are unable to solve this, just let me know through the forum. Okay, you have to use only muxes, yeah, and inverters can be used if you want to. Okay. So if no one has a doubt in this particular question, let's move on to the next question. Okay, so we are given 3 muxes and we need to figure out what is the combinational, what is the function that is being performed by this particular combinational circuit. Okay, so the thing is, it is visible to us what it is performing, right? So it's basically a 4 cross 1 mux. Okay, but let us say the architecture is not so clear to us. So let us say that this is some random block and it is not given as a mux. So what should be our approach to solve such a question? Okay, so in this particular question, it is clear that it's a 4 cross 1 mux, right? But let us try to see step by step how we need to solve it. So the basic equation will again remain the same. Okay, so this equation, and just like how we solved for this node and then this node, the same thing we are going to do for this particular question as well. Okay, so let me call this as node y1 and this as node y0. Okay, so we are just using some nomenclature for our convenience, that we will be able to solve the equations in a better way and we will have clarity on what that equation represents. So I just put y1 to represent that it is going to the input i1, and similarly I put y0 so as to represent that it is going to input i0. Okay, so what will be the equation for y1? Can anyone tell me?
It is S bar I3 plus S I2.
Okay. Is there any other solution for this one? Y1? Is there any other answer?
It is S1 bar I0, sorry, S1 bar I2
Okay.
plus S1 I3.
S1, I3. Okay. So is everyone, so does everyone agree to this particular answer? Okay. So the thing is, the correct representation of y1 will be this one. Okay, S1 bar I2 plus S1 I3. Okay, so as I mentioned, so whenever you take the bar, you have to take the thing. So this is basically 0 and 1, right? So if you are taking S, then you should be taking, so if you are taking S bar, then it should be I0, right? And I0 is connected to I2, so it will be S bar I2. Similarly, plus it will be S I1, right? And I1 is connected to I3, so it will be S I3. or if we write it as 1 and 2, so we can write it as S1 bar I2, S1 I3. Is that one clear?
Yeah.
Okay. Similarly, for Y0, what we can do is, we can do the same thing here, right? So Y0 will be S1 bar I0 plus S1 I1. Okay. Then the final function f is presented as S0 bar I0. Okay, so this is I0 is connected to Y0 plus S0 Y1. Okay, now what we need to do is, we just need to replace Y0 and Y1 in this equation. Okay, after that, simply just we need to expand it. S0 bar S1 bar I0 plus S0 bar S1 I1 plus S0 S1 bar I2 plus S0 S1 I3. Okay, so we can observe that it represents a 4 cross 1 mux. Okay, so this is the equation for a 4 cross 1 mux. Correct. Now we can say that, okay, yeah, this 4 cross 1 mux thing is correct. So I0, I1, I2, I3 are the inputs, S0 and S1 are the selection lines. So let us say, instead of these muxes, if you are given a certain block of combinational logic, so you need to do the same thing. So at each of the intermediate nodes, you try to figure out the equations in terms of the inputs, okay, and try to solve the final equation for the output, right? So if you have anything in this particular format, okay, then you can clearly state that it's a mux. Okay, and so here it represents if 0 0 is selected, if 0 1 is selected, I1 will be selected, if 1 0 is selected, I2 will be selected, if 1 1 is selected, I3 will be selected. Okay, I hope this particular method is clear. So the solution is straightforward, it is mentioned, but this method is important. So I hope that is clear. Yeah, does anyone have any doubt in this question?
No.
Okay, thanks. So let's move on to the next question. Okay, so in this question what we are given is, so what we need to implement is a 5 to 32 decoder, right? And what it is asking us is what components can we use to implement this particular thing. Okay, so here we will have 32 outputs. This is 0 1 2 3 4. Okay, okay, otherwise let me use some name A B C D. Okay, so looking at the options, yeah, Anshu, you can unmute yourself. Yeah, does anyone have a doubt? Okay, yeah, So what we need to implement is a 5 to 32 decoder. Okay, so okay, let us try to look at the outputs first, because we'll focus on this number 32 for some time. So can this 2 3:8 decoder give us a 32 output? Of course not, right? Because let's say we put both of them here, so the maximum outputs that we can get is 16. So option C is not correct. Okay. Similarly, can 4 3:8 decoder give us the output? Yeah, probably it can give us. Okay, because let's say we place 4 blocks here in this way. So this can give us 8 output, this can give us 8, this can give us 8, this can give us 8. So 4 3:8 is possible. 8 2:4 is possible. Yeah, it is still possible. But now let us try to look at the possible implementation that can be done. Okay, so if we take 4 3:8 decoder, okay, and we are placing it in this fashion. Okay, so can you think of a topology in which we can have only 5 inputs and 32 like outputs from these combinations? So you can take it up as an assignment again, and you will observe that that is not feasible with using 4 3:8 decoders. Okay, only 4 3:8 decoders. So what we need to do is, let us focus on this one, 1 2:4 decoder. Okay, yeah, and there is another catch. So these decoders, they can have an enable, decoder enable, like only when that enable signal is high, then only that decoding will take place, right? So let's keep the 4 3:8 decoders in this fashion. Okay, so this will satisfy our number of decoding lines that is required. Dot dot dot, this is 7. Similarly, let's this 7, this will be 8 to 15. Similarly, this will be 16 to 23. So this will be 24 to 31. Okay, so here we have the 32 outputs. But now these are 3:8 decoders, right? So where will these 3 lines go? And we have a 2:4. Okay, yeah, so here you can observe that we have 4 intermediate outputs, right? So what we can do is, we can connect them to the 4 decoders that is available, and this is the decoder enable. I am writing it as E. Okay, so these 3 inputs, they can be straight means directly connected to the inputs that is coming from this block. Okay, so this is the final block that we need to implement, and we are already supplied with these inputs A, B, C, D, E. Okay, similarly we can do for this block as well. Okay, I can name it A, B, and this is C, D, E. Okay, so let me explain this one a bit in an elaborative way. So let's say when AB is having a particular value, let's say AB is 0 0. So what will happen is, this line will be high, and if this line is high, this particular decoder will be selected, Okay, and if this particular decoder is selected, then we will look at the lower 3 bits, that is C, D, E. So let's say C is 0, D is 0, E is also 0. Then this 0th line will be selected. Okay, similarly, let's say A, B is again 0, 0, C is 0, D is 0, E is 1. Then what will happen is AB is 0, 0, so it means the first decoder will be selected, and remaining 0, 0, 1, so it means the first line of this first decoder that will be selected. Similarly, you can go on and check for all the decoders that are available. Let's say if I select something like 1, 1, 0, 0, 1. Okay, so according to this thing, which one should be selected? So let me convert this into decimal so that it will be easier for us to represent. So 1, 1, this will be 1 plus 1, this is 8, 8 plus 16, 24, 25. Okay, so it means the 25th line should be high. It means here, right? So AB is 1, 1. So 1, 1 means decoder number 4 should be selected, like this decoder, right? After this is selected, we look at the lowermost bits, that is C, D, E. Okay, so C, D, E 0, 0, 1. So 24 is 0, 0, 0. So just after 24 will be 0, 0, 1. So that is 25. So we can similarly we can state that option A, that is 1, 2 is to 4 decoder and 4, 3 is to 8 decoders can do our work. Okay, so here one thing you need to note down, that is decoder, when it is stated as a decoder, you can like easily assume that it's a decoder with an enable logic. Okay, is this problem clear, or does anyone have a question in this problem? Okay, then we can move on to the next question. Okay, so here we have to find out the XS3 code of decimal number 9. Okay, so XS3 code is not a weighted code, and for finding out the XS3 code, so we have two simple steps. One thing is, whatever number is given, you just add +3 to it. Okay, this is step 1. Step 2 is you convert the number into binary. Okay, so let me give an example and then I'll suggest you to solve this question on your own. So let's
Answer A.
No, A is not the correct answer.
Sorry, B.
B. Okay, yeah, B is the correct option. So the first thing that we need to do is, let's say I have a decimal number given as 1. Okay, so using the first step, what we need to do is 1 plus 3 is equal to 4. Okay, then you convert this into binary. So you can convert this into binary. 4 is 0, 1, 0, 0. Similarly, for this particular question, the decimal number that is given is 9. So 9 plus 3, that is 12. Now step 2 is convert this 12 into binary, that is 1, 1, 0, 0. Okay. Okay, so can anyone tell me why, so what is the use of this XS3 code? Any guesses? So this is a bit difficult to guess, but did anyone try playing around with the XS3 code and observe anything? Okay, if not, okay, then let me reveal it. So basically XS3 code, it helps us in performing subtraction. So the thing is, XS3 is a self-complementing code. It means that whatever number you take, if you take the ones complement of that number, so the number that you will arrive at will be the nines complement of that particular number, and using nines complement you can perform subtraction, right? So for performing any form of like decimal subtraction, we don't need to use several things in the hardware, right? So okay, let me give an example here. So let's say I have a number 5. Okay, so what will be the XS3 code of this one? So 5 plus 3 is equal to 8, right? So 8's binary is 1 0 0 0. Okay, so now if I take the ones complement of this number, that will be only inverting the bits, 0 1 1 1. Okay, so 0 1 1 1 is actually the XS3 representation of, can anyone tell me 0 1 1 1 is the XS3 representation of which number?
4.
Yep, so 4. So 0 1 1 1 is the XS3 representation of 4, and this is actually the nines complement of 5. Okay, so using this representation, what becomes easier for us is the subtraction process. Otherwise we would have used a very complicated hardware to perform the subtraction, but here if you observe it, we only need to invert the bits to get at the nines complement, right? So that's the beauty of XS3 code, and that is why it is very relevant if this particular function is kept in mind. Okay, so moving on to the next question. So yeah, so the next question is a bit similar to what we have previously solved. What we need to do is we need to find out how many 3:8 line decoders with enable outputs are needed to construct a 6:64 line decoder. Okay, so the first thing that we need to see is what are the number of outputs. Okay, so the number of outputs required is 64, right? And how many outputs can a 3:8 decoder give us? 8.
8.
Yeah, so we have 8 outputs and we need 64 outputs. So what we can do is simply 64 by 8 will be the number of decoders that are required at the output end. Okay, so we have our output end ready. So this is okay, I made it a bit big. Let me, okay, 0 to 7, similarly dot dot dot, it will be till 63. Okay, so the next thing is we have to select from each of these 8, any one has to be active, right? So what we can do is we can place another decoder at the front. Okay, so let us assume this is 0 to 7 and it is connected to the
For enable inputs.
yeah, similarly this is connected to this. Okay, so how many total inputs were needed? 6. Okay, so we have A, B, C here, and the other inputs will be D, E, F here. Okay, similarly these things will also be connected, and it will follow the same pattern that was followed for this particular question, right? Question number 4. Okay, so let us solve this one. So at the output we need 8 and at the input stage we need 1. So total,
C, I think.
yeah, C is the correct option.
Yeah.
So 8 plus 1, 9. Okay, so does anyone have a question in this one, this numerical? Okay, if not, then we can proceed to the next question. Okay, so in question 7, what we need to we need to answer this particular question, that we have to implement multiplication of two 2-bit numbers. Okay, so let us say that 2-bit numbers is let's say a and b, and let me write the bits as let me write the bits as a1 for the most significant bit and a0 for the least significant bit. Similarly, b, I'll write it as b1 b0. Okay, so when I write a1 a0, so in the mind you can take an example, like it can be 0 1. So if I take 0 1, then 0 is representing a1 and 1 is representing a0. Okay, similarly you can assume 1 1 or anything. I'm just representing it in a very generic notation, so that the hardware that we will be making is also generic. Like, it should not cover only few cases, it should be applicable to all the 2-bit cases. Okay, so let's perform multiplication in b into a format. So when we perform multiplication, we write it as this, right? Okay, we have a solution. Let's see if that is correct or not. Okay, so this particular bit will be okay. So you imagine this, that we are having two numbers already, two 2-bit numbers. What should this bit be if I am representing the 2-bit numbers as b1 b0 a1 a0? Can anyone answer what this place should occupy?
It is A0, B0.
Yes, it is a0 b0. Similarly, this one,
B1, A0.
correct. Okay, so what should be this bit?
This bit is A1, B0.
Yeah, and this bit,
A1, B1.
yeah. So after we so these are actually called as partial products. Okay, why partial products? Because we are taking half of the bits and we are generating these terms. Okay, so let me call it as c0, this result. Okay, let me call this result as c1. So actually the summation of this result is c1. Then let me call whatever result we will have here as c2, and let me put a blank space here and call it as c3. So can anyone tell me if c3 is needed or not?
Yeah, for carry, if there is any carry,
Yeah.
which is needed for that.
Correct. So can anyone tell me if c2 needs a summation, or can we directly write it as a1 b1?
We need, in addition, if there is a carry from C1,
Yeah,
second bit to third bit, we may have to perform a half adder addition.
correct. Okay, so here we can see that we need two adders, right? So let me write it as adders and gates. Okay, so adders we will need two for sure, because c1, this is straightforward, c1 is present here, so there needs to be, so there are two terms and we have to reduce that term to arrive at c1, so there will be one adder, then the next adder that is present at c2. So as it was mentioned by one of the participants, that the carry that is resulted from c1, so it also needs to be added to this particular term to generate c2, right? So for that purpose we will need a plus, we will need a adder, right? So there are two adders that are needed. Okay, similarly, what will be the number of gates that are needed? Okay, so the first thing is, to generate all the partial products that are present here, we will need gates. How? Okay, so I'll represent that using an example. So let us say I take 1 0 into 1 1. Okay, so 1 0 into 1 1 will be 1 0, and here it will be 1 0. Okay, so it is 0 1 1. So how did this one become 0? We multiplied this with this. Here you can observe this is basically doing an AND operation, right? One of the input is 0, another input is 1, so this is 0. Okay. Similarly, how we did 1 1, it's the same thing, it's an AND operation, right? So basically 1-bit multiplication is basically you are taking AND of those two inputs, right? So it means to generate each of the partial products we are using AND gates.
Yeah.
Correct?
We need 4 AND gates.
Correct. So there are 4 partial products, so there will be 4 AND gates. Okay. So yeah.
C, I think, is the right answer.
Correct. C is the right answer. Actually, someone said A. So A won't be possible because in A only 2 AND gates are mentioned, right? And yeah, also full adder is mentioned. So full adder maybe you can use, but so always prefer the option that is minimal in nature, right? So 2 half adders can do our job. So why should we go for a 2 full adder? Okay, so 4 AND gates and 2 half adder, that will do
Yes.
our job. So option C is correct in this one. Okay. Does anyone have any doubt in this question? Okay, I hope that this particular thing is clear, because this is how any other arithmetic circuit, let's say you are asked for a 2 3-bit numbers, okay, and you have to mention what are the number of adders and gates that are needed to implement that 3-bit multiplication. So you should be able to do that. Okay. So this, again, as I mentioned, the process should be clear. So arriving at the answer is a different thing, but the process by which we arrive at the answer is more important. And this thing, like, I treated things to be in a generic fashion. Otherwise, if you observe this particular case, let's say I took 1 0 and 1 1. So in this case there is no carry from this bit to this bit. So if someone takes an example and then they try to solve for this answer, they may arrive at a different solution. So it is always preferred why we choose the half adder. Okay, so here you can see the maximum number of inputs is always going to be 2. Okay, either in this case or even in this case, right? So we need to use the half adders. I mean, had there been a case where we could have required 3 inputs to be resolved into sum and carry, only in that case we will need a full adder. Okay, so yeah, you can also make an argument that, okay, I can use a full adder here, right? You give these 2 inputs to here, and this one you can give 0. Yeah, of course you can do that, but as I mentioned, that you have to search for the minimal viable option that is available with you. So in this case, half adder can do the same job. So why should we go for a full adder? Does that answer your question? Okay. Okay, so moving on to the next question. Okay, so the number of input lines in a common BCD to 7 segment decoder is dash. Okay, so can anyone answer this question?
It should be 4, right?
Yeah, it's correct. So option D is correct. Okay, so let me explain this solution. So the solution lies here. Okay, sorry, the solution. Yeah, so the thing is, we need a BCD to 7 segment decoder, right? So the BCD, it can have values from 0 to 9. Okay, So 0 is 0 0 0 0 and the maximum is 1 0 0 1. So total 4 bits are there. So there will be 4 lines needed. Okay, that will go to that 7 segment decoder. Okay, I mean this is a bit straightforward. So okay, moving on to the next question. Okay, so in the next question what we need to do is we need to perform addition of two given numbers in BCD. Okay, so okay, let me explain what is BCD. So let's say you must have observed, like we have in any board or something, we have something like this, right? Okay, so this is the 7 segment display that we were talking about. Okay, so this is segment 1 2 3 4 5 6 7. So that's why this is called as a 7 segment display. So this particular thing, it can only display you numbers from 0 to 9 in terms of maximum value 9. Okay, if all the lines are on, it will appear as a 8 to you, right? So it can show you 9 like this. Okay, so actually, so one of this, if you take one of this block, that is a BCD. So the range of these numbers are from 0 to 9. So similarly, you'll ask me, what if we have to represent two numbers, means two digit numbers?
Answer is A.
Okay, let's see if that is correct. Okay, so yeah, so as I was mentioning, so if let's say you have a two digit number called 22, so how will you represent it in BCD? What you need to do is you need to create a separate block that represents 2 and the other separate block represents 2. Like, so this block should be decoded as 0010, this one should be decoded as 0010, and not your conventional binary number. Like, you can't do the long division method here to arrive at the BCD numbers. Okay, you treat each decimal separately. Okay, so now moving on to the question. So we have to add 96 and 69 in BCD. Okay, so 9 6 plus 6 9. Okay, so we have, the first thing that we need to do is, do not convert 96 into decimal or 69, sorry, do not convert 96 into binary or 69 into binary using the long division method, because these are representation in BCD. So treat each of them as a single digit. Okay, so 9 will be represented as 001. Okay, 6 will be represented as 0110. Okay, similarly this 6 is the same thing, 0110, this 9 is 1001, and you have to perform addition of these numbers. So this will be 1, this is 1, this is 1, this is 1, 1 1 1 1. Okay, so someone mentioned that this is the final output. Okay, but what does this particular combination represent in BCD? BCD number, as I mentioned, it goes from 0 to 9, right? So what will this number represent in BCD? It is an invalid number.
Yes.
Correct. So what we need to do is, whenever we arrive at any number that is greater than 9 in BCD, we add 6 to it. Okay, so 6 is basically 0110 to make it a
110,
correct, to make it a valid BCD number. So let us do the same thing in both the bits. Okay, so here we will add 0110, here we will add 0110. We will have 1, this is 110, this is 3, so 1 1, this is 0, this is 1 1 1 0 1, this is 3 1 1, this is 0. Okay, so now what we have is a valid BCD number. Okay, why we add 6 for correction and why not any other number? Okay, so the maximum value for 4-bit representation that we will arrive at is 6. Right, means the final number is 9 in BCD. Okay, so the maximum value that a 4-bit number can represent is 15. Correct? And the invalid number starts from 10. 10 can't be represented in BCD, right? So 9 is the maximum number. So it means after you cross 9, okay, let me give an example like this. Okay, so you see this is the number 9. Okay, so after incrementing, what should the digits be? It should be 1 and 0. Is that clear? So 1 will represent 0001 and this is 0000. Okay, now you check what is the increment. Okay, so let us do it in a simpler way. So what does this one represent? It represents 16 in decimal, right? But
Yes.
what is the binary representation of 10? Okay, let's not go into the binary representation. Let us play around in the decimal itself. So 10 is 10. Okay, so you see the difference between BCD representation and decimal representation. So BCD representation would have been actually 16 in decimal, and in the decimal, like when we normally increment it, it would have been 10. So the difference is actually of 6 bits. Is that point clear, Srimukhi? Okay, so yeah, so here we have arrived at the solution, that is 1 0 1 1 0 0 1 0 1. Yeah, option C is the correct answer. Okay, does anyone have any question in this particular numerical? Okay, and is this concept clear why we added 6? So that's a very good question someone asked. So why exactly 6? Why not any other number? So I tried to explain it using this analogy that like let's say there is a BCD number 9, and had it been in let's say any other number system decimal, so it would have been 10, but in what is it called? Yeah, but in BCD it is 1 and 0. Right, and 1 and 0, if you convert it into decimal, it will be 16, and 10 would have been in decimal. So 16 minus 10, that is 6. So we need a correction factor of plus 6. Right. So I hope this particular question is clear. Does anyone have any doubt? Okay, let's move on to the next question then. Okay, so here we need to find out the BCD equivalent of 3, 4, 5. So can someone tell me what is the BCD equivalent of 3, 4, 5? Because we have solved a question just before this question.
Option D, I think.
Option D. Okay. How did you arrive at this particular option?
Because the BCD of 3 is 011, 0011 in 8421 code, and then 4 is 0100, 5 is 0101. That's
Correct.
right.
Yeah. So option D is correct. Okay, and yeah, the reasoning is also correct in this question. Okay, so moving on to the next question. Is my screen changing? Is it, or is it stuck?
Yes, it is changing.
Okay. Yeah. Okay. So let us look at this particular question. So consider the output A and B with I0, I1, I2 and I3 as input and A and B as output. Okay, so let us say we have a black box and we know what are the inputs: I0, I1, I2, I3, and we have two outputs, A and B. Okay, so what we need to tell is what is this particular black box. Okay, and what are the hints that are available with us? One thing is it mentions what A is, and another thing is it mentions what B is. Okay, so whenever you arrive at such a question, the first thing that you need to do is draw the truth table. Okay, okay, so in this case, in neither of the equation I0 is used. So let me make a truth table with only three variables that are used in these equations: I3, I2, I1. Okay, then output will be A and B. Okay, so let us write the input variables, like it will be from 0 to 7. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so if I3 is 0, I2 is 0, I1 is 0, what is A? A is 0 because A is a combination of I2 and I3, right? Similarly, what will be B? B will also be 0. I3 is 0, even though I2 bar is going to be 1, but I1 is 0, so B is also 0, right? Similarly, what will be the next one? I2 bar is, okay, A is 0 anyways because I3, I2 both are 0. But what is B? B, I3 is 0, but I2 bar will be 1 and I1 is 1. So 1.1, B is 1. Okay. Similarly, what is the next one? 0, 1, 0. In 0, 1, 0, I1 is 0. So B is going to be 0. And I2 is 1 in A case. So it is 1. Okay. Next, A will be, okay, for 0, 1, 1, A will be 1 because I2 is 1. Okay. And B will be 0 because I2 bar will be 0, right? Similarly, for 1, 0, 0, A is going to be 1 because I3 is 1, and if there is a OR and if you observe one of the bits to be 1, then the entire equation is going to be 1, right? So it is 1. Then B is, okay, sorry, B is also 1 because I3 is there. Similarly, this one is 1, then again I3 is 1. Okay, so the remaining bits are also 1, 1, right? So let me reduce this table a bit further. Okay, and now let me include I0 as well. I3, I2, I1, I0, A, B. Okay, so when this condition arises, okay, so 0, 0, 0, and because I0 is not present, so it doesn't matter whether I0 is 1, I0 is 0, because it doesn't play any role in these two equations. The output is anyways going to be 0, 0, correct? Now, if let's say it is 0, 0, 1, and because I0 is not present, I can put a cross again. So it is going to be 0, 1. That is this particular condition. Okay. So if it is 0, 1, okay, when we observe that I2 is 1, okay, irrespective of what I1 is, the output is 1 0. Okay, observe these two cases, right? So irrespective of what I1 is, so we don't care about I1 and we never cared about I0. So let us put a cross here. The output is going to be 1 0. Okay, and when we observe that I3 is high, then we don't bother about I2, I1, and I0 we never care about it. So it doesn't matter whatever I1 and I2 is. If I3 is 1, it is going to be 1 1. Okay, so we don't care about this, we don't care about this, we don't care about this. Okay, I3 is anyways visible that it is getting the highest priority, because you can observe that I3 is present independently as a summation term. So if anything is present as a summation term independently in both the equations, it means that it is getting the highest priority. So whatever means, if that value is 1, it doesn't matter whatever other terms are present, the output of the equation is going to be anyways 1. Okay, so here you can observe that if the highest bit is 1, then it doesn't matter what the rest of the bits are, the output is going to be 1 1. Okay, similarly if I2 is 1, then we don't bother about I2 and I0, the output is going to be 1 0. Similarly I1 is 1, it doesn't matter whatever the other thing is, it is going to be 0 1. And if all are 0, we don't bother about I0, it is 0 0. Okay, so what is this particular circuit called as? Can anyone answer?
Demultiplexer it is.
No, it's not a demultiplexer.
Priority encoder.
Correct, it's a priority encoder. Okay, because here we can see the highest bit getting the highest priority. Okay, so if the highest bit is set, we don't care about the rest of the bits. Like in this case, highest bit was I3 was set. In this case, I2 was set. I0 is 0. I3 is 0. So in this case, I1 is set, so we didn't bother about I0. So this kind of gives a priority to the highest bit if it is set. So that's why it is called as a priority encoder. Okay, I hope this question is clear. Does anyone have any doubt in this question? Okay, this particular method is also clear, right? Like whenever you have the function, you draw the truth table, try to reduce the truth table and observe the pattern, and accordingly you decide what circuit is and what function it performs. Okay, then the next question is the number 267 would be represented in, okay, I think it is BCD. Yeah, so we need to represent 267 in BCD. Again, it's a straightforward question. So can anyone?
Option A. Option A.
Option A.
Option A is.
Yeah, option A is correct. This is 2, this is 6, this is 7. Okay. So yeah, we have covered all the problems that I planned to cover today. So let's revisit whatever we tried to cover. So in today's session, what we did is some problems on multiplexers, some problems on priority encoders. So okay, one problem on priority encoder, then a few problems on decoders, then XS3 code and what were its significance. Okay, so these are the things that we covered today, and all of these are combinational blocks, right? None of them it involves a memory anywhere. And these combinational blocks, the building blocks are logic gates, but it is having a form of abstraction. So the benefit of having a form of abstraction is you can simply plug and play them around. You don't need to divide that multiplexer into AND gates, and then like it looks a bit clumsy and complicated, right? So we need some form of abstraction. Okay, so the first question that we solved is we were given a set of 2 cross 1 muxes, and we were supposed to implement 16 cross 1 muxes. We were supposed to find the number of 2 cross 1 muxes that are required, and we also showed how they should be arranged so as to get a 16 cross 1 mux using 2 cross 1 muxes. So this is the best example so to how to synthesize a circuit, right? So if you are falling short of 16 cross 1 muxes and you have 2 cross 1 muxes with you, you can just synthesize a 16 cross 1 mux if you are clear with the digital logic that is going behind. Okay, the next thing that we did is, okay, so we can implement any function that we want using a combination of multiplexers, right? And we saw how. So we took a standard reference multiplexer, we tried to come up with a equation for that particular multiplexer in this format, and this reference equation we tried to use it in the circuit that was shown to us. We tried to solve the value for A, okay, with the inputs as y and 0, and we found the value for A. Then what we did is we saw that there was an inverter, so that A will travel as A to the input 0, but it will travel as A bar to the input 1. Okay, then we did the same thing with F. So F also we tried to construct this equation. Okay, so okay, there's some line here. Okay, so we tried to construct this equation using this standard reference. Okay, then what we did is we simply replaced A with these values. Okay, and then we solved the equation. Like we just opened the brackets, and can we change A and B in the standard reference? Yeah, sure, you can change that. So let's say you call it something else, y and x. You can mention it as s bar y. So this is just for your reference, s bar x. Is this what you meant? Or if you meant whether you can replace B here and A here, yeah, you can do that. Accordingly, the equation will also change. If this is the case, then it will be S bar B plus SA. So what I want to mention is, like, if you are taking the complement of the select line, so select whatever is connected to this input. Okay, and if you are taking the non-complement version, connect it to anything like whatever is put in this particular input. Is that clear? Okay, so the next thing that we did is this depends on the 0 and 1. Yes, it depends on the 0 and 1. Okay, let me tell you why. So let's say in this case, if s is equal to 0, okay, so for this our original example where I have connected A to 0 and B to 1, okay, so if s is equal to 0, then A is going to be selected, right? So how do I represent this thing as an equation? If s is equal to 0, select A. Okay, it means if there would have been an output, so y will be 0 whenever s is not selected, like s is equal to 1, right? But y will be A whenever s is equal to 0. Correct. So if s is equal to 0, then y is becoming A in this case, right? Omkar, is this particular point clear? Okay, so, and that is the reason. Similarly, if s is equal to 1, you select B, and if I have to put it in equation form, I have to write y is equal to SB. Okay, and a mux implements both of them in one at a time wala operation. So that's why we represent this in the form of this out is equal to S bar A plus SB equation. So what matters is what is connected to 0 and 1. Okay, so the next question that we tried to solve is also related to multiplexers, and though the answer was visible to us that it was 4 cross 1 mux, we chose the road not taken, and we tried to solve it in a way that will help us to solve any circuit that is thrown at us, right? So we tried to figure out the intermediate node equations. We tried to solve those intermediate node equations, and we tried to solve what is going to be the output. Okay, so my suggestion is, if you are well practiced with these equations, that you can figure out what this entire black box represents. You don't need to go through all the procedure. You can directly say that this is a 4:1 mux. But let us say you are given a combination of circuit. Let's say you have a AND gate, you have a mux, okay, then you have another mux which is connected in this way, and then there is stuff and stuff. Okay, so how will you solve such a complicated circuit? So the thing is, you first figure out what are the intermediate node equations, then gradually from those intermediate node equations you arrive at the output, just like we did it in this case. Okay, so this is actually a very good practice that you can develop, and it will help you out in the future when you try to solve bigger and complicated circuits using multiplexers. Okay, so the next question that we solved is related to decoders, and we were supposed to implement a 5 to 32 decoder, and we checked which option was the most suitable one for us, and we observed that, and yeah, here we needed to keep one thing in mind, that whatever decoder that is available with us, it can be treated as a decoder with an enable input, right? So enable is basically, if enable is high, then that decoder is functioning. If it is low, then that decoder is not functioning, right? And what we did is we put a decoder at the input, okay, and we gave 2 inputs to that decoder, which will give out all the enable signals to the respective decoders, okay. And the first thing that we observed is the output. Okay, there are 32 decoding lines that should be coming out of our black box, so that's why I figured out that, okay, so 32 means total, it can be either 8 cross 4, means it can be either 3:8 decoders in 4 numbers, or 2:4 decoders in 8 numbers, okay, or any such possible combination. And then accordingly I started arranging them, okay, in this fashion that it works, and we verified that it is going to work. Okay, so if 0, 0 is selected, this decoder is selected. If 0, 0, 0 is selected, then this particular line of this decoder is selected. Okay, then someone can also say that if 0, 0, 0 is selected, because C, D, E represent 0, 0, 0, so this line will also be active, right? But no, that's not true, because here 0, 0 is only selected, so this will be enable, not this. Even though the input to this decoder say that you select 8, but the enable says do not select anything unless I'm enable. Okay, so that's what is this 5 to 32 decoder wala circuit. The next thing that we did is related to XS3 code representation. So we learnt what are the steps to represent a decimal number in XS3. First you add 3 to it. Next you convert whatever is present in decimal to binary. Okay, similarly 9, we first added 3, that becomes 12, and then we convert it to decimal, binary, sorry. Okay, so the next question was, it was similar to the one that we solved before, 5 to 32 bit decoder, but in this case we were asked how many 3:8 line decoders with enable output, yeah, it was mentioned in this case, are needed to construct 6 to 64. So the first thing that we did is, so if we need a 64 output, so and if we have 8 outputs available with us, then what we do is 64 by 8. So how many decoders at the output? So we got 8 decoders at the output. Okay, and then we also saw that how many needs to be enabled at a time. Okay, so we can use 1 decoder at the input, and 1 plus 8, that was total 9 decoders required. Okay, yeah. So the next question was related to implement. So this is a question from arithmetic circuits, and we needed to implement a 2-bit multiplication operation using 2 bits. So here I just represented 2 bits in a very generic format. I called them A1 A0 and B1 B0, and we performed the multiplication operation, and we observed like how that multiplication operation actually happens. So we are used to multiplication operation we are so comfortable with multiplication operation that we sometimes forget that how these products are being generated. Okay, but in this case I took a generic example to demonstrate how these products are generated and how does the carry propagate, right? So, and then we observed why this generic representation is needed, because if you take any particular case, okay, let's say if someone takes 0 0 0 0, then he or she may say that we don't need any adders at all because there won't be any carry, but that's not true, right? So if you are making a 2-bit circuit, you need to ensure that it is functional for all the possible cases. So that's why I took a generic circuit, and we observed that there are 2 half adders that are needed. Yeah, and then there was another question that why half adders, why not full adders? So yeah, the minimum viable option that is available with us, we should go for that instead of the bigger one. And yeah, so 2 adders and total 4 gates. So we observed that the partial products can be generated by using AND gates, so they will behave as a 1-bit multiplier. Okay, so the next question was related to BCD to 7 segment, and we observed that BCD total 4 digits are needed, so the number of input lines that are needed is also 4. Okay, then the next thing that we did is we added 2 numbers that are present in BCD, and the addition was performed in BCD. We arrived at the solution in this way, but this is invalid because there is no representation for 1 1 1 1 in BCD, right? So what we did is we added 6 to make it a valid representation. Okay, and we arrive at C as the solution to our answer. Then there was a question why 6. I mentioned that the last valid bit, the last valid digit in a BCD is 9, and if let's say there is an increment by 1, so it will be 1 0. So 1 will be represented like this, and 0 will be represented like this in BCD. And if I convert from BCD to binary, then it is going to be 16 in binary, right? So this is the decimal equivalent of that 16, and the original number would have been actually 10, because if you increment from 9 it is going to be 10. So the difference is 6. It means I need to make a correction of 6, right? So that's why I added plus 6 here, plus 6 to this digit. Okay, then this is the answer that we arrive at. Okay, then the next question was a bit straightforward, looking at the problems that we have already solved. So we just needed to represent 3 4 5 in BCD. So 3 is 0 0 1 1, 4 is 0 1 0 0, and 5 is 0 1 0 1. So this was also straightforward. Then the next thing was related to so we were given a black box, and we needed to figure out what this black box does from the given equations, right? So the first thing that we did is construct the truth table. Okay, next thing we did is reduce the truth table, and then observe what it actually does. And we observed that this actually implements a priority encoder, right? So these bits are getting encoded into 2-bit representations. right? And we observed that the highest bit, if that is set, we don't bother about the other bits that are present. So that's what gives it the priority. Okay, then the next question, okay, so the last question was also a simpler one. We needed to represent 2, 6, 7 in BCD representation. Okay, so we can see that this is 2, this is 6 is basically 0, 1, 1, 0 in BCD, and 7 is 0, 1, 1, 1 in BCD. So these are the questions that we covered today. And yeah, so the recorded lecture, it will be available on the YouTube channel. So this complete lecture, it was being recorded and it is available on the YouTube channel after 5:30 or something. These slides will also be shared with you by the NPTEL team, along with all the annotation and the solutions that I have mentioned here. And what I will suggest is, whatever questions we have solved today, try to solve it without looking at the solution. Okay, so this will in a way help you, like whenever you are stuck at something, or if you have a particular doubt that okay, this is the answer that you are arriving at, which is yeah, sure, I will share the channel name. Okay, so this is my channel. Okay, and yeah, no problem. So yeah, so as I was suggesting that try to solve these problems on your own, and if you arrive at a different solution from what we have solved in this particular session, so you can check what makes the solution different. Is it something, if there is a mistake, or maybe there's a different solution that is actually possible, or else if you arrive at the same solution but with a very faster method, then that's a very great thing, and you can use the efficient one out of the two solutions. So yeah, it will help you in a lot of other ways as well. Yeah, so that's what we had for today. If anyone has any doubt related to whatever we have solved today, or anything related to the portion that we have covered, just let me know. Okay. Yeah. Does anyone have any doubt in the questions that we have solved today? So you can feel free to unmute yourself to discuss that problem. Okay, if yeah, if you don't have any doubt, then yeah, is whatever we have covered in today's lecture, is that clear? Okay, thanks. Is there any point where you felt that it was not covered properly, or maybe you need another explanation for that? Any question? Okay, then that's the end of today's session, and I'll still be around here. So just let me know if you have a doubt in any of the question. Feel free to ask it. Okay. So thanks everyone for joining. Hello. So we have completed the problems that we discussed in today's session. So, do you want to give me a summary, Ajay?